This is exercise 8.9, applications of series. I'm not going to do some of the easier questions at the beginning because I think you'll be able to cope with those. I'm going to start at question 8. It says, in a game, a child starts at point P and then runs and picks up an apple 3 meters away. She then runs back to P and puts the apple in the bucket. The child then runs to the next apple, which is 6 meters away because it's 3 plus 3, and then runs back to P to place it back in the bucket, and this continues until all the apples she has all the apples in the bucket. Now, to get the first apple, she runs 3 meters. To get the second apple, or I'm not sure if it's a boy or girl, but the child runs 6 meters for the second apple. So here, for the first apple, the child runs 3 times 1, which is 3 meters. For the second apple, the child runs 6 meters, which is 3 times 2 is 6 meters. The third apple, the child runs 3, 3, 3, which is 3 times 3, which is 9 meters. So therefore, to collect the kth apple, so I'm only looking at the forward direction. It just says how far does the child run to get the kth apple, not how far has the child run in total. So we're just looking at a term. So to get the kth apple, it's 3 times k, which is 3k meters. That's how far the child runs to get the kth apple. Now, for part B of the question. Part B says, how far does the child run to fetch all k apples, including return trips to P? So remember, the child starts at a point, then goes forward and back, and then goes forward and back, and forward and back. Now, we can do this 2 ways. We can either say a return trip's going to be double the 3 meters, so a return trip is 6 meters for the first one, then the second return trip will be 6 plus 6 is 12. So the first return trip is 3 plus 3, which is 6, and the second one is 6 plus 6, which is 12. And the third one is 9 plus 9, because it'd be 9 forward, 9 back, which is 18. This is one way that we could have a look at it. So to fetch all k apples, including return trips, we could either just do 3 plus 6 plus 9, do the sum of all of those ones, and then double it at the end, or we can do 6 plus 12 plus 18, which includes all the return trips. I think I'll do the second way because each it is asking to get all the return trips, not just some of the forward or some of the reverse trips. So we've got 6 plus 12 plus 18 plus. We know that to get the kth apple, it's 3k one way. So therefore, the return one would be 6k, okay? Plus 6k. Now, we know that there are k trips, okay? So there are 2 ways that we can sum this series up. 2 ways of working out the distance the child runs to get all the k apples, including the return trip. So we know that n is k. We know that a, the first term, is 6. We know that the common difference is also 6. And so we could do sum of n terms is n on 2, 2a plus n minus 1 times d. Now we know that n is k, so it's k on 2. So sum for k return trips is k on 2. 2 times a is 12, so it's 2 times 6, which is 12, plus k minus 1 times the common difference is 6. So this becomes 12k on 2, which is 6k. Sorry, I'm going to keep the k on 2 out, separate actually. K on 2, let's just expand. 12 plus 6k minus 6, which is k on 2, 6 plus 6k. And if I take out or if I expand here, I get 6k on 2 plus 6k squared on 2, which is 3k plus 3k squared, which is the answer, which is written as k bracket k plus 3k. That's how the answer is written. Now that's one way of doing it. Now that's if you didn't realise, I suppose, that the last term is 6k, but if you do realise that the last term is 6k, you could have said sum of k terms is, or s, sum of n terms is n on 2, use the formula n on 2, a plus l. So sum of k terms is k on 2, a is 6, and l, the last term, is 6k. And if we expand here, we get 6k on 2 plus 6k squared on 2, which is again the same answer, 3k plus 3k squared, or k bracket 3 plus 3k. Or I could even put the 3 outside, actually. 3k bracket 1 plus k if we wanted, okay? But yeah, or even that's fine. So we don't really need that, okay? So that's how far the child runs to fetch all k apples. So it could have been done 2 different ways. And now for the last part of the question, it says the child runs 270 meters to fetch all the apples and returns them to the bucket. How many apples are there? So we know that the sum Sn is 270 meters. That's all the distance run to fetch all the apples, and we have an expression for Sk. So therefore we've got 270 equals 3k plus 3k squared, and we can divide through by 3 and take everything actually over to the right. So we've got 3k squared plus 3k minus 270 equals 0. Dividing through by 3, we've got k squared plus k minus 90 equals 0. Factors of 90 will go plus 10 and minus 9. So therefore, yes, that gives us 10k, yeah, 1k. So therefore k is negative 10 or k is 9. But therefore k equals 9, as k has to be greater than 0. So how many apples were there? There were 9 apples. Okay, we'll just look at another example. In another question, question 6, it says a timber fence is to be built on sloping land, like this, with the shortest piece of timber 1.2 meters and the longest 1.8 meters, and there are 61 pieces of timber in the fence. And the first question is, what is the difference in height between each piece of timber? So you know your shortest is 1.2 and the tallest is 1.8, so you'll subtract those, but then you've got to see what you need to divide by. Now if there are 61 pieces of timber, there's only 60 spaces between them, because if you look at 2 pieces, there's 1 space. If you look at 1, 2, 3 pieces, there are 2 spaces. If you count 1, 2, 3, 4, 5 pieces, how many gaps are there? 1, 2, 3, 4 spaces. So to look at the difference in height between each piece of timber, you'll subtract 1.8 minus 1.2, which is 0.6, but then you'll need to divide it by 60, not by 61. So we've got 1.8 minus 1.2 is 0.6 meters. So this is question 6. And part A, the difference between each, in height between each piece of timber. Now that's 0.6 meters is actually 60 centimeters. So the difference between each piece of timber is 60 centimeters divided by 60, which is 1 centimeter difference in height, okay? So we'll now look at part B. Now the next part of the question says what length of timber is needed for the fence altogether. So if you want, you can remember that 60 centimeters divided by 60 is 1 centimeter, or you could have just kept it in meters. 0.6 meters divided by 60 is 0.01 meters. So you can actually just keep it, in meters if you want. Otherwise you're going to have to go and change all your units. So I think we'll just keep it in meters. So we've got 1 centimeter, which happens to be 0.01 meters. So our series looks like this. The shortest is 1.2. And then the next piece is 1.2 plus 0.01, which is 1.21. And the next piece will be 1.22. And then we know that the longest piece is 1.8. So, and we know that the first and the last term, and we also now know how many pieces of timber there are, so just be very careful here because there are actually 61 pieces of timber. So A in this question is 1.2, L, the last term, is 1.8, and N, the number of pieces of timber, is 61. So therefore the total length of timber needed for the fence is the sum of these 61 terms, which is the formula Sn is n on 2 a plus L, or you could use the formula Sn equals n on 2 2a plus n minus 1d. So it's 61 over 2, a is 1.2 plus L is 1.8. And so it's 30.5 times 1.2 plus 1.8 is 3, which is 91.5 metres. So therefore that's the length of timber needed for the fence altogether. So just be very careful in questions like that, where it's really easy to make that mistake of dividing by 60 or dividing by 61. So you just need to be careful there. At question 10 in exercise 8.9, it says a southern brown bandicoot population in Western Australia is decreasing by 5% each year. And the question is, what percentage of the population is left after 5 years? Okay, now with this question, you're going to have to come up with a starting amount. And you can call it X, or you can call it 100, or whatever you like. I'd probably use 100 if you want, okay? So you can do it a few different ways. We can try it a couple of different ways. So question 10, if you've got, let's say, 100% of your population at the beginning and it decreases by 5% each year, then 5%, so the first one will be 100. Your second value will be, after 1 year, you'll only have 95% left. So remember so it's 100 times, if you want to decrease by 5%, you times it by 95% or by 0.95. The third term will be whatever that is, times another 0.95, so reduce it again by 5%, and so on. Okay, so basically what we've got is 100 for our first term. We can put commas if we want, okay, rather than pluses, okay. I'll do that, comma, comma, so that I'm writing it as a sequence if I put commas. So 100, then we've got 100 times 0.95. Actually, I will go back and put pluses, I prefer pluses. Then we've got 100 times 0.95 squared plus ... Okay, so we've got our first term, our second term, our third term, etc. Okay, now it says what percentage of the population is left after 5 years. So you have to think, so first of all, is it an arithmetic or a geometric series? It's clearly a geometric series. So this is a geometric series with A equal to 100 and R, the common ratio, each term is being multiplied by 0.95. Now, it says what percentage is left after 5 years. So therefore, when n is 5, do you want to know the sum, or do you just want to know what the fifth term is? And you just want to know what the fifth term is. It's Tn equals AR to the n minus 1, which is 100 times 0.95 times to the power of 5 minus 1, which is 100 times 0.95 to the power of 4. We can already see that we'd have that because term 1 is just 100. See, this is term 1, this is term 2. Term 3 has power of 2, term 4 will have power of 3, and term 5 will have power of 4, which is what we've got. So the percentage of the population left after 5 years, we'll just evaluate what this is. Stake there. That's the first term, but that's the original time. This is after 1 year, after 2 years, after 3. So we actually need, when n, we want the sixth term. So after 5 years, we actually want when n is 6, because it's the beginning. After 1 year, after 2 years is actually t3. So just be very careful with that. So it's 6 minus 1. So we want 100 times 0.95 to the power of 5, which is approximately 77.4. So therefore we will say 77.4% of the population is left after 5 years. Okay, so just be really careful with those as well. Okay, now part B says, after how many years will the population be only 50%? So we want the term that's going to be equivalent to 50%. So we want Tn to be equal to 50. So we know that Tn equals AR to the n minus 1, which is 100 times 0.95 to the n minus 1. So we'll put 50 is equal to 100 times 0.95 to the power of n minus 1. 50 divided by 100 is 0.5 equals 0.95 to the power of n minus 1. Now taking logs of both sides, we've got ln 0.5 equals ln 0.95 to the power of n minus 1, which is n minus 1 times ln 0.95. That's ln 0.5 equals that. So therefore n minus 1 is equal to ln 0.5 over ln 0.95. Now both of those are negative. Log of anything between 0 and 1 is negative. So negative divided by negative will be positive. So therefore n minus 1 is, so n minus 1 is 13.51, which is, so therefore n is 13.51 plus 1, which is 14.51. So therefore, as we were looking before, back up here, term 1, term 2 is after the first year. Looking up here. Term 3 is after the second year. So if we want 14.5, we're looking at, therefore, it is after 13.5 years, because when t, say, is 13.5, sorry, when t is 14.5, like when we get 14.5 as our answer, that's after 13.5 years. Okay, so just be really careful with those, okay? So therefore, it's after 13.5 years. And part C says, how many years will it take for the population to decrease by 80%? So therefore, if population decreases by 80%, then there's only 20% remaining. So we'll be doing the same thing as we did before, but we want Tn to equal 20. So 20 equals 100 times 0.95 to the n minus 1. 20 over 100 is 0.2 equals 0.95 to the power of n minus 1. Taking logs of both sides and just jumping an extra step, we'll get that. And so therefore n minus 1 is ln 0.2 over ln 0.95. So therefore n minus 1 is, n minus 1 is 13.4, so n is 14.4. So therefore, as we were just saying before, that it will be after 13.4 years, because when n is 14.4, that means that 13.4 years has passed, because n is 1 is at 0 time. Sorry, I've just written my numbers around wrong. If you just see here, I had 31.4, so I just wrote that out wrong. So I'll just fix that now. So this is actually, sorry, not 13.4, it's 31.4. So that will be 32.4. But remember, the 32nd term is 31 years, so it's 31.4 years. Sorry about that, getting a bit late again at night. Question 11, it says to write 2.81 recurring as a fraction. Now we know that 2.81 is 2.818181, etc., which is 2.81 plus 0.0081 plus 0.000081, etc. Now, that is 2.81 plus, actually what I'm going to do is even break it up further, so it's 2 plus 0.81 plus 0.0081 plus 0.000081, etc. So what we're going to do, we can see here that we've got a geometric series there, not including the 2. So therefore it's going to be 2 plus this geometric series here. Now to get from one term to the next, you're dividing, so the difference between this and this, you're dividing by 100, but remember common ratio is not about division, it's about multiplying. So here I've got A is 0.81, but my common ratio is, say, T2 over T1. And if you divide these two, you get, so to go from 0.81 to that term, you multiply by 0.01, which gives you 0.0081. And to get from 0.0081 to this other term here with the 4 zeros, you're multiplying by 0.01 again. So this bit here is a series with A equal to 0.81 and the common ratio 0.01. So therefore, what we've got here is 2 plus, and this is a sum of a series here. So 2 plus, remember it's a geometric series, common ratio is less than 1, so it's 2 plus a r to the n, no, it's 1 minus r to the n over 1 minus r. So it's 2 plus a is 0.81 times 1, actually girls, or class, it's actually a sum to infinity because it goes on forever and ever and ever. So it's 2 plus a over 1 minus r, because remember, sum to infinity is a over 1 minus r. So it will be 2 plus 0.81 over 1 minus 0.01, which is 2 plus 0.81 over 0.99. Sorry, just running off the page there. So it's 2 plus 0.81 over 0.99, which is 2 plus 81 over 99, multiplying the numerator and the denominator both by 100, which is 2 and 81 over 99. Now, I know that you know how to do this from using other methods that you learnt in year 11, but this is writing it as a fraction using geometric series. Okay, sorry about the little errors here with this sum to infinity, but that does go on, remember. It's a recurring decimal and it goes on forever, so it is a sum to infinity. Now, question 14. Now it says an 8 centimetre seedling grows by 4 4/5 centimetres in the first week and then keeps growing by 3/5 of its previous week's growth. How tall will it grow? Now, if we start with 8 and we times it by 3/5, we get 24 over 5, which is 4 4/5. So that's how much it grows by. So in other words, it's growing by 3/5 of its height in that first week. So the original height is 8, and then it grows by 4 4/5, and then it's going to grow 3/5 of the previous week's growth. So actually, I'm not going to write it like that. So I'm going to go 8 plus 8 times 3/5, which is the 4 4/5, plus it's then going to grow 3/5. So this is its growth for the first week. It's then going to grow 3/5 of this, which will be 8 times 3/5 times another 3/5. And then that will just continue, plus 8 times 3/5 cubed, etc. Now each of these is, so that's the initial, that's how much it grows by, and that amount actually equals 4 4/5, and then we times this 4 4/5, which is 8 times 3/5, by another 3/5, so that's shown there by 3/5 squared, etc. So here we've got that A is 8, it's a geometric series. So we've got a geometric series with A is 8, R, the common ratio, is 3/5. And because our absolute value of R is less than 1, a sum to infinity will apply here. So there will be a limiting sum. So the question is, how tall will it grow? So they're asking for the sum to infinity is a over 1 minus r. They're asking for the limiting sum, which is 8 over 1 minus 3/5, which is 8 divided by 2/5, which is 8 times 5 over 2, which is 20 centimetres. So therefore that seedling will grow to 20 centimetres tall. Okay, this is question 19. Mary bounces a ball, dropping it from 1.5 metres on its first bounce. So it starts up here, goes down 1.5 metres to the ground, and then it rises 2/5 of its height each bounce. So it comes back up 1.5 times 2/5, and then it goes back down. Now it has to go back down that same distance, 1.5 times 2/5, and then it comes back up. But it comes back up 2/5 of that, which is 1.5 times 2/5 squared, and then back down that same amount, 1.5 times 2/5 squared. And then it comes back up 2/5 of that, so it'll be 1.5 times 2/5 cubed, and then back down that same amount, 1.5 times 2/5 cubed, etc. This ball will eventually, it'll just keep going up and down. Now that we know that won't happen, it will eventually stop. But according to this model, because it's going 2/5 of its previous height, it will continue. It'll theoretically never stop, but we can do a sum to infinity here. So notice that all of these double ups we have, except for the first one. So we've got a double there, a double up and down there, a double up and down here, etc. But the first one is not a double. So therefore the distance through which the ball travels, so the total distance that the ball travels will be 1.5 plus 2 times the sum to infinity, because it's up, down, up, down. Now this is what we've got here. We need to look at this second series that we've got. So we've got 1.5, then we've got, now that one doesn't get doubled, so I want to keep it separately. Plus, we've got 1.5 times 2/5 plus 1.5 times 2/5 squared plus 1.5 times 2/5 cubed, but these ones are all doubled. Okay, so remember here we've got a geometric series with a equal to, so we're not going to include this because it's not doubled. So here is my first term. A is 1.5 times 2/5, and r is another 2/5. Okay, so therefore the total distance travelled is 1.5 plus 2 times sum to infinity, as we set up here, which is 2 times a over 1 minus r, which is the 1.5, that's that 1.5 on its own, plus 2 times a is 2 times 1.5 times 2/5 over 1 minus r, which is 1 minus 2/5. So that is 1.5 plus 2 times 1/5. 2 times 1.5 is 3. 3 times 2/5 is 6 over 5. Over, so I'm just keeping this 1.5 separate, over 3/5. So 6/5 divided by 3/5 is 6/5 times 5 over 3, which is 2. So it's 1.5 plus 2, which is 3.5 meters. So therefore this ball bounces through a distance of 3.5 meters. Okay, so now I'm going to get you to look at exercise 8.9, and I think I'll get you to do exercise 8.9 question 2 and question 3, and I think we'll look at we've looked at question 6. We'll look at either, I think we'll do question 4, 2, 3, 4. Won't worry about 5. We've looked at 6. You can do question 7. And we've looked at 8. And you can do question 9. So I'm writing these all down so you can get them in a minute. Then you can try a couple from 11, maybe do question 11C and 11G, and I'm thinking 11I. And I'd be trying to do as many as I can from the others because you need practice with them. So you can do question 12. Maybe 15 and 16. Or actually make it just 16, not 15. 12, 16, 17, 18, and you can do 20 and 21. So I've written those down, so I'll just put them up now. So with this last exercise, if you could please do exercise 8.9, question 2, 3, 4, 7, 9, 11, C, G, I, question 12, 16, 17, 18, 20, and 21.